Alright, so problem 25 is trying to trickify you, make you feel like, oh my god, I'm on an incline, it's gonna be tricky. But no. So, part A, um, we are just basically trying to figure out the how far from the top equilibrium is. Well, equilibrium, as you well know by now, is a balance of forces. No torques going on. So we got spring force pulling up the ramp, gravity component Fgx going down the ramp, and so at equilibrium, Fgx and Fs are equal. Hopefully you've memorized this by now, so you don't have to do the geometry every time. Fgx is sine of the angle of the ramp, and spring force is kx. We're going to do the magnitude of the spring force, so direction doesn't matter there. And we know everything except x. I didn't list the givens. I'll do it in here right now. The mass is 14. Don't forget 9.8. Oops. The angle is 40 degrees. The spring constant is 120 newtons per meter. X, solve for x, and you get 0.075 meters, but that's not, we want the distance from the top of the incline. And in the problem it said that the relaxed springs position, so you got relaxed, we're like holding the block on the ramp, then you let go and stretches out a bit and comes to a new equilibrium. Same ramp, just a different situation. So we just figured out basically x is this, but we want the distance from the top. So we could add that, the equilibrium, these two are the same. Equilibrium, the relaxed length, which is 0. D is x plus relax, which is 0.075 plus 0.45, and that equals 0.525 meters. Part B is actually completely unrelated to this because, well, first off, part B wants us to find the period of oscillation. So now that it's in equilibrium, we grab it, pull it down a little bit, and let go, and it's going to go doing, 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 oscillate back and forth, right? If there's no friction, it'll do that forever, and the amplitude won't decrease. So the period of this type of motion with a mass on a spring is the same as always, m over k. But I think one of the points of this problem is to have you realize that it doesn't matter that the spring is on incline, it's got gravity doing crap and all that. This is the period regardless. Gravity just shifts the equilibrium, but this is the period about the new equilibrium, right? So the forces are balanced now. So yeah, that's really all it is. And we know all these things. 2 pi root 14. Oh, whoops, I just realized something. In the problem, I hope I didn't confusify you, they gave you the weight. I should have looked at my notes more closely. This is the weight, which is mg. You guys, some of you might have been thinking, why did you add the 9.8? That's the weight. Good catch. Sorry about that. But to find the mass, you have to divide the weight by the acceleration due to gravity, and so we need to take care of the 9.8 here, and this is 120. So the period is 0.686 seconds. And yeah, so just let me emphasize one more time that the period doesn't depend on other forces. You may think, doesn't this only work when there's just spring force acting on it? And the question is no, this works when you have something like a spring allowing oscillations, and something like a spring with a spring constant, and the period of that is about an equilibrium position. So sometimes, for example, if there's no friction and you have a block horizontally on a floor, you can be in equilibrium. The spring can be in equilibrium with no outside forces necessary, like no pulling this way or anything. So in this case, you just have a spring force. Same equation to find the period. Here, you have gravity in addition to the spring force, but once you're in equilibrium, they cancel out and this period works. Anyway, that's the key to this problem. Alright, next up, 28.